Hello. 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 Hello, everyone from Gandhinagar University. My name is Saurabh Srivastav, and it's my privilege to be here and giving a small talk about my journey, my education, where I belong to, what I work on, why did I choose this field of science and technology. First and foremost, I would like to thank Dr. Swasti. She's a very good friend of mine, and thanks for giving me this opportunity to discuss things which I do with all of you at the Gandhinagar University. And I would also like to thank Dr. Dhawal Chudasama for the communication and setting things up. So I'll start with my introduction. My name is Saurabh Srivastav. I come from Gorakhpur, UP. Um, and my background has been science and mathematics. So I did. Ah, hello. और अच्छा ठीक है। मेरी आवाज़ कुछ भी सुनाई दे रही थी कि नहीं? ओके, ठीक है। Hello everyone from Gandhinagar University. My name is Saurabh Srivastav, and it's my privilege to present about my work with you and talk about how does the innovation work in physics and material science department. I'll talk about physics and material science because my background is that. Throughout my life, I love doing science, and I chose physics as my career. But first and foremost, I would like to thank Dr. Swasti Saxena, esteemed professor at your university, for reaching out to me and asking me to if I can deliver a talk. So thank you, Swasti, and also just for a little information. Dr. Swasti's husband Ankite has been very good friend of mine, and we have been together for almost. We know each other from our university days, like in Gorakhpur University. Also, I would like to thank Dr. Dhawal, who has been communicating with me with about this talk. So without further ado, let me start my introduction. My name is Saurabh Srivastava, and I come from Gorakhpur in Uttar Pradesh. I have done my schooling until my university, Master of Science in Physics department at Gorakhpur University, and then I moved to IIT Kharagpur to do my master's in technology, and then I moved to Canada for my PhD. Currently, I'm working in Singapore as a senior scientist at an organization here. Just like CSIR in India, we have an agency here. It's called Agency for Science, Technology and Research, and this agency has a lot of institute to work on different fields, different projects, and all. One of the institutes is called Institute of for Material Science and Engineering, short from IMRI. So I have a small presentation for you guys. Let me share my screen and then we can go forward from there. So let's talk about Exploring innovation from fundamental particles to functional materials. Uh, Starting with Singapore. Singapore is a very small island on the southeast of India. It's so small that one side it's about 40 kilometers, another side is about 35 kilometers, which so Singapore kind of is smaller than probably your Gandhinagar or maybe your Vadodara. This is the institute where I work on. You can see A star. It's called Agency for Science, Technology and Research. Again, going back to where I did my schooling, where I did my PhD and all. So I did my MSc in Gorakhpur University. Then I moved to Kharagpur for MTech. Then I went to Canada, University of Waterloo for my PhD in nanotechnology. Later, I moved to Massachusetts Institute of Technology for my postdoc. And from there, I moved to Singapore in National University of Singapore. And for last 3 years, I'm working with A-Star now. So the agenda will be today's agenda will be discussing about physics and how it is connected to material science, why it is important in our daily life, and why should we choose it as a career. So I'll give you some idea about the current research trends which are cutting edge, and also some real world applications where you can apply your knowledge of physics and material science. So physics basically helps you understand the natural laws. How does that work? If you see laws of motion, laws of thermodynamics, Maxwell equations, these are the basic physical formulas which helps you understand the behavior, the universe, how the universe behaves, from the motion of planets to the till the behavior of subatomic particles. Also, you have quantum physics, which explains the chemical bonding. Then you need to understand thermodynamics if you want to study biology or meteorology. Then you have semiconductors and electronics. You are surrounded by semiconductors and electronics in your life, starting from your cell phone to your television to your vehicles to your computers. Everything is based on semiconductors. Then you have the importance of physics and physics in medical devices, where you have MRIs and X-rays. They are all built on these principles. Also, space technologies and satellites and everything. So you need physics at the core. When you look at the material science, everything requires material. Every single technology requires materials and engineering of those materials, starting from civil engineering, where you develop concrete, steels, composites, you develop ceramics, you develop polymers. In electrical engineering, you develop semiconductors, insulators, superconductors. At the same time, materials, since material science is a combination of physics, chemistry, and biology, and at the same time mathematics. Like it's a field of science where everything comes together to form uh, from the materials for which can be used to innovate different application, which can make your life easier, like breakthroughs in material science, such as transistors, where your smartphones have lots of microchips which are based on transistors. You have biomaterials, where you can develop artificial organs and artificial bones also, which can be used in implants if you go through some accident, or if you are born with some deficiency, you can actually use biomaterials to develop those implants. Then at the same time, you have smart materials which can be used for making sensors and actuators. You can develop solar cells using these manipulative behaviors of these smart materials. Uh, then why it is important in today's time? Because you need to combine everything together to develop something. Physics can help you understand the basic concept, basic laws of the nature, and basic nature of those materials. But how do you combine those? Material science tells you, material science and engineering tells you. And that's where you develop cutting edge technologies, and that's where you tackle the real world problems by applying those knowledge. All right. This is one of the labs where I work on. It's called clean room. You can see all these guys are wearing blue suits. They are all covered up from top to bottom, because most of the devices, most of the electronic devices you are developing in these kind of labs has to be dust free, because those devices are even smaller than the dust particles. So even one dust particle can destroy all your devices. And imagine you are, let's say, if you are talking about transistors, we have billions and billions of transistors per unit area, like per inch. So the size of those transistors are much, much smaller than the dust particles. So we want to have a dust-free environment, right? These these clean rooms can be classified in different classes, which are not important here, but just to give you an idea that this is a dust-free environment. That's why we have to cover up everything when we work on that. There are some tools which are used to develop things, which are used to innovate things, starting from, let's say, you are making frames, or you are making fabricating the devices, or you are characterizing those devices. You have so many different types of tools which can be used. A thin film deposition tool can be called physical vapor deposition system. I'll show a couple of tools which I used during my PhD in Canada. And then you have characterization tool like transmission electron microscopy, for looking at the samples at atomic scale. Then you have to do chemical analysis. What kind of materials, what kind of elements are present in your particular device or particular material? You can use XPS and XRD tools. Then you have other tools which are used to fabricate those devices, especially in nanofabrication range, where your device size is very small. You have photolithography, you have ion beam lithography. At the same time, you want to electron beam lithography. At the same time, you are testing those devices using probe stations, UV visible spectroscopy, AFM, so many other. There are many other tools which can be used for characterizing those devices. So yeah, basically innovation is a challenging job, but at the same time you produce something which are used for you which are used to develop things for consumers. So starting from your cell phone in your pocket till supercomputers, satellites, and everything is developed using these kind of tools. So in your daily life, whether you go for construction, you go for computer coding, whether you want to do weather prediction, whether you want to do advanced farming, transportation, or medical, everywhere you need the combination of physics and chemistry and mathematics and biology. Combinedly, it's called interdisciplinary material science, right? So now I'll come to something which I like to do and which I have done in my last 15 years of research in the field of material science. I'll show you three different examples. One example is, let's say, memristus. Memristus are basically non-volatile memories. And how we generate these devices, let's look at this. So memristos are, you might have heard of terms like transistors or inductors, or resistors or capacitors. There was one, so if you see here, resistor, capacitor, and inductors, these three are correlated somehow with voltage and current, charge and voltage, and flux and current. There was one element which was fundamental element which was missing, that connects your flux with your charge, because flux is flow of charge with respect to time. All these elements, they don't have the time component, but the fourth one can have time component. And when you introduce time component here, you create a device which memorizes its history of voltage and current flow. So basically, memristor is a resistor which has a memory. And what kind of devices have memories? Your pen drives, your computer has RAMs, you have hard drives in your computer. They all have memories because you store your data there. And in current stage, all these devices are three terminal devices. Somehow these memristors were made two terminal devices, so you can have multiple stacking of these memristor to create 3D electronics. So in future you can have 1 terabyte of data in your phone, in your computer, and you don't need to reboot these data. Because the problem is when you store the data, you basically supply voltage, and when you turn off the computer, the all the data is gone, especially in your RAM. So RAM is a volatile memory. So retain the data in your RAM, you need to supply voltage again. But in memristor, you don't need to supply any voltage. It still contains your data. And there has been a tremendous effort in creating these memory devices for future generation computers. We have done some good work to generate these kind of devices, which have been excellent in their performances. Probably I won't go too much into detail, but these are some of the devices which will be in the market very soon, and you will have much faster, even mobile phones. Your chips are very fast, so all kind of things which you do with supercomputers, you can actually do with your mobile phones. Then, since these are two terminal devices, you can increase the number of devices per unit area, and then you can stack them to have lots of memory in your computer. In the second case study, let's talk about the display. So why you see colors on your screen is because you have three different colors of pixels, which is called R, G, and B: red, blue, and green. And these three are the fundamental colors. When you combine them together, you get white light. And because of those white signals, you get all the video, whatever the video signal is sent to your to your screen, you see different colors. So there are different ways where you can generate these RGB displays. One of the ways is called using quantum dots. So quantum dots have different emission wavelength. Okay, so if you create a blue LED based on indium gallium nitride, and when you start putting different wavelength emission of quantum dots, you can generate different colors. So you see, if one light is emitting blue color, if other is emitting red, and other is green, and other is emitting red, at the center you will see white color. And that's how all these LEDs in your television or your phones are working. So this is where you can apply the concept of material science, where you are tuning the properties of your materials by applying the laws of physics and chemistry. So you can generate a lot of pixels, smaller pixels of these quantum dots, and you can actually increase the resolution of your displays, especially when you are making smart displays like your smartphones or your smart watches or even projector displays. Lots of materials engineering is involved there. Again, you can see if I combine three pixels together, I can see a white light. And this is one of the diagrams where you get the colors. So currently, most of the TVs we have, they give the colors in this triangle. So anything within this triangle, you generate these colors. But however, you cannot generate all these colors. That's why the resolution is not perfect. But if you're using quantum dots, you see this larger triangle, you can cover as many colors in this triangle as possible. So that's why in the current trend, if you look at quantum dot LEDs or organic LEDs, they have much higher saturation of colors and resolution. There's third study where we are developing meta lenses. Basically, what meta lenses are, they are as good as your normal lenses in imaging. So any kind of camera in your phone, in your DSLR, in even in any kind of camera where we take the images, the properties of those cameras are to focus the light at a particular point at their focal length. But now, to focus the light at the particular length, you need to have a curvature of the lens. You guys have heard of convex lens and concave lens, where they have a curvature. The reason for that curvature is to focus the light, right? But if you want to have the same focusing capabilities at flat lenses, then you have to do some kind of nano engineering on the surface. So these lenses are usually flat, but they can still focus, and they at the same time they remove lots of aberrations which are part of these curved lenses. And at the same time, the importance of this emerging technology has been increasing tremendously. And in the future, you will have all kind of imaging devices made out of these metamaterials. One of the most important phenomena of these meta lenses are you can actually get negative refraction, where light. So when the light goes from one medium to another medium, it bends a little, but it doesn't bend on a negative refraction. However, using these meta lenses technology, developing this, you can actually have a negative refraction, which will have new types of applications in the imaging industry. Just to compare, you have conventional these lenses where you have a curvature on the top. You see the thickness of the lens. At the same time, if we generate meta lenses, our thickness has gone really down. So one, it doesn't take much space to install them. Two, it's very lightweight. And third, it has very high optical efficiency. So your imaging resolution is very good. These lenses can be used for making tunable lenses, large aperture lenses, holographic devices, aberration-free lenses, and all. There are different techniques where you can make these lenses. I won't go into much detail. I'm just listing them here. Also, so these making these lenses will enable you to have a wide angle lens. So imagine you have a standard lens in your camera which can see up to 40 to 50 degree. You have an ultra wide lens in your camera which can see up to 100 degree, but anything above this you cannot see. Meta lenses have the capabilities to see much wider. It can even go to 180 degrees. And how we make it? Basically, we have substrate, and then we do lots of nano engineering. You see, this is how the electron microscopy image look like. And when we zoom in, we have these kind of pillars, nano pillars. And that's how we generate the images. We create many other different lenses to be used in medical technology. So this lens was used in smartphone. These lenses will be used in medical technologies, basically in brain endoscopy, where you need surgery. So these lenses are very applicable to image the cancer cells or tumors in the brain. One more application of these lenses are basically removing the chromatic aberration. So if you have a conventional lens, basically your different wavelength of the light focuses at different planes. But if you have meta lenses, they are actually focusing on one point. You see, so without meta, it's called meta corrector. Without meta corrector, you have these red, green, and blue shift. But once you put the meta corrector in, your images are very sharp. So with a single device, with a single meta lenses, you can remove all kind of aberrations, starting from chromatic aberration, spherical aberration, and at the same time, your optical efficiency is very high, and your cost is low, your weight is very low. So these kind of lenses will be used in space technology, where these lenses will be installed in the camera in satellites. So we have different types of designs, different types of fabrication process to generate all these kind of lenses. So these are the three case studies. Uh, these were my team in Waterloo. This is my team in Singapore, and so basically now if I come back to life here with my face. not I'm sure some of you might have enjoyed this talk, and it will encourage you to take technology and science, choose as your career, so you can go further and innovate something which can be used by consumers, which can help consumers. Be it in space technology, be it in semiconductor industry, be it in imaging technology, be it in medical. Uh, I've been very happy working on different research fields, and there's a lot to do. There are lots of gaps where you can come in and fill in. So, and I'm available for you for any kind of guidance or questions you have. Looking forward to seeing some of you going into this field and making your career as a good scientist or good professor, and all the very best. Thank you.